Matter, as we know it, consists of stars, gas, nebulas, the Earth, or even us. But would you believe me if I tell you that this only makes up 5% of the total mass in the universe? There are other things that we aren't taking into consideration, such as dark matter, dark energy. Such things are invisible to our eyes. So we can actually say that we only perceive a tiny fraction of reality. But actually, it gets even worse because we don't know what dark matter is, or what it does, or what are its properties. So this video will try to figure out the true meaning of dark matter.
There has been an anomaly and we haven't discovered what it is yet. Galaxies in our universe seem to be achieving an impossible feat. They are moving and rotating at a speed such that the gravity generated by the visible matter cannot possibly hold them together, so they should have thrown themselves apart a long time ago. But roughly, 80% of the mass of the universe is made up of a material that scientists cannot directly observe. Unlike normal matter or bright matter like stars, it does not emit light nor energy. It means it doesn't interact with the electromagnetic force. This bizarre ingredient is known as dark matter. But what is dark matter? It is an element that doesn't absorb or reflect light either, making it extremely hard to spot. Peter Van Dokkum, a researcher at Yale University, said in a statement that the motions of the stars tell us how much matter there is, but those motions doesn't care about its form. They just tell us that some kind of matter is there. And how do we know that dark matter exists if we can see it? This is because of the gravitational effect it seems to have on visible matter. Based on the momentum conservation principle, we can clearly see that if the total momentum at the beginning and at the end at a proton-proton collision is not equal, this means that there must be an invisible particle that is carrying away that missing momentum. Also, in the 1970s, scientists calculated the mass of the large objects in space by studying their motion instead of their size. But for example, instead of finding two stars that travel at the exact same velocity ending up at the same spot, they will always find those stars ending up at two different locations, this indicating that the galaxies contain even more mass than the one that could be seen.
One of the currently unknown questions: what is dark matter made of? Dark matter has three characteristics. It is massive. It means that it must have a certain mass. Stable. Cannot be broken down into other particles. It must also be cold. It must move at non-relativistic speeds. I will start with one of the most popular candidates, the weakly interacting massive particles, or WIMPs. The most interesting about WIMPs is their origin, because they are the particles that were left after the Big Bang. A possible WIMP could be the neutralinos. This is one of the new particles not yet discovered proposed by supersymmetry. We also have candidates far removed from the idea of WIMPs, like axion. The axion is a hypothetical particular scalar that was proposed to solve the so-called strong CP problem. It is estimated that the mass of the axion is tremendously small, making detection quite complicated. The neutrino might be the ideal candidate if it weren't for the third condition. The neutrino falls into the category of hot dark matter. But dark matter candidates don't have to be just particles. Primordial black holes have also been taken into account.
To finish, I want to mention other candidates from which dark matter could be formed, like stellar neutrinos, Kaluza-Klein, and Needle-Higgs.
An interesting question we could focus on is in the existence of some dark forces. Initially it was thought that the gravitational force was the only one that interacted with dark matter, but scientists of the Durham University in England have published in the monthly notices of the Royal Astronomical Society the first signs that dark forces might actually exist. The researchers used the multi-unit spectroscopic explorer on the Very Large Telescope in Chile, along with the Hubble Space Telescope, to study the Abell 3827 cluster, where four galaxies are colliding. This study suggests for the first time that dark matter may be interacting with itself through an unknown force other than gravity, and it has no effect on ordinary matter. For dark matter to interact with itself, it would require the existence not only of dark matter particles, but also of a dark force governing their interactions and dark bosons transmitting that force. To determine this hypothesis, astronomers used a natural phenomenon called gravitational lensing, predicted by Einstein's general relativity theory. The dark matter in Abell 3827 is abundant, so it deforms the space around it. This means that when light from a distant object behind the cluster travels in the direction of the Earth, as it passes through this area, it distorts and produces gravitational lensing features such as arcs of light and double images, which astronomers use to measure the invisible matter in the cluster. By this information, the scientists discovered that in at least one of the colliding galaxies, dark matter had been separated from stars and other kind of visible matter by about 5,000 light years. And one explanation for this is that the dark matter of this galaxy interacted with the dark matter of one of the other galaxies. These interactions slowed it down, causing it to separate and leave the irregular matter behind. It could also be that only a part of dark matter interacts with itself, while most of it behaves like traditional particles. Despite this hypothesis, we cannot assume the existence of dark forces, since no signs of self-interactive dark matter have appeared in other galaxy collisions, so we have to continue making observations to groups of individual galaxies until this situation occurs more frequently in order to support this idea.
The biggest problem until now in astrophysics is dark matter. We are not sure whether it exists or it doesn't exist in our universe. When astronomers and scientists add up all the matter in the sky, such as gas, stars, galaxies, it isn't enough to explain the behavior we can see. Those stars and galaxies are moving faster than they should be. Scientists came up to the agreement that something else is creating a gravitational force strong enough to keep them together, something that we cannot see and we aren't taking in consideration. In 1884, Lord Kelvin was the first one to take into consideration the theory of dark matter. He was measuring the velocities of the stars in the Milky Way galaxy because he wanted to figure out if it was a stable system or not. By doing this, he was equaling the kinetic energy the stars had to their gravitational energy. When he was doing his experiment, he was able to calculate the amount of mass the system should have in order to be held together. But when he performed his calculation, he figured out that there was mass missing that we were not seeing. He named this missing matter dark matter and said there were dark stars that weren't shining. Those stars would be the mass that was missing in the Milky Way galaxy. In 1933, Lyric Zwicky made a similar experiment in which he measured the velocity of galaxies moving around clusters. He noticed that the velocity was very quickly and it was almost impossible for them to keep gravitationally bound. He figured out that there must be something that was interacting with gravity that was holding them together. Furthermore, he also found the mass-to-light ratio and found it to be 100 times more than the mass we actually see in stars. He then concluded the presence of dark matter in the galaxy. Now let's talk about the first direct evidence of dark matter. This was in the beginning of the 2000s and was called the bullet cluster case. What was happening is that two clusters of galaxies were colliding together, and in these types of collisions, we would expect all the gas to collide, heat up, and glow in X-ray form. But in this particular case, the galaxies go past each other, and the ordinary matter seems to be separated from the dark matter. If we remember the theory of Einstein of gravitational lensing, we can see that any type of matter will be deflected and bent. Light going behind the dark matter will be bent and deflected. And by the lensing effects, we can determine the distribution of mass. As we can see in this picture, we are able to notice that all of the matter is in the blank space. It's not in the visible matter as we would expect, or in the X-ray or in the stars. So there was the conclusion that something is going on. There is dark matter in the universe. Overall, there must be some additional matter that we're not seeing, whose gravitational pull is strong enough to keep those stars moving at that speed and not flying away. For example, when you spin a bicycle wheel with water, very quickly the droplets would go away. That is what we would expect to happen to the stars and the galaxies if there wasn't something else stronger holding them together.
As we already talked about, lots of cosmological observations agree that there is a kind of invisible matter for us, given that it does not emit nor absorbs any kind of electromagnetic radiation. But it has to exist, and that approximately 80% of the universe is composed by this theoretical substance. otherwise there would be a lot of missing matter in our galaxy. Now, it is believed that dark matter could decay into ordinary particles, but this anomaly is still a mystery, and one of the most important questions that arises with this topic is if it is really possible that particles that we can see and analyze are product of dark matter, and that if the decaying of dark matter could help us to decode its composition. Unfortunately, we don't really know the answer, but there is a lot of models trying to explain these issues, such as the stereo neutrino dark matter model, which postulates that if dark matter could decay into ordinary particles, it would emit X-ray photons detectable. In fact, there have been many positive detections around the Earth that can be considered as a proof for the decaying of dark matter, but also negative detections that deny this proof. So it is not strongly confirmed that dark matter decays. Nevertheless, some of the most important candidates for its composition, according to Bertone Gianfranco, are the supersymmetric neutralino and the Kaluza-Klein excitations. At the end, there is still much more questions waiting to be solved. But it is clear that a way for understanding this ongoing mystery is for sure a great step for us to have a minimum clue of what is going on in the universe.